Welcome back. The objective of this video is to explore implicitly defined functions, and we'll separate that from an explicit or explicit form of a function, and we've got some review here of relations and functions as well. And also in this video, you'll see equations of circles and hyperbolas, some of the recent things that we've studied as well. So the term for a set of ordered pairs, x and y, is called a relation. When the relation relates a single value of y to each value of x, this relation is known as a function. And we know that as for a single x value, we can only go to one y value. We can't have different x's or the same x going to different y's. And then that wouldn't be a function. That would be something that would fail the vertical line test. So if you solve the equation for y in terms of x, then we write it as y equals f of x. So y in terms of x means we've got y equals, and on the other side we have all the other stuff. And we say that that function is an explicit form. So we've been doing that already, but now we're just titling that. In general, when a function f is defined by an equation in two variables, x and y, we say the function is implicitly defined. For example, a function like x squared minus 2y equals 4 is implicitly defined. You've seen where many curves fail the vertical line test. Circles, ellipses, hyperbolas, and cannot be classified as functions. Recall that a unit circle, x squared plus y squared equals 1, is centered at the origin and has a radius of 1. And 0, 1 and 0, negative 1 are both solutions, so it's a relation and not a function. Here we have the same x value going to two different y's. So in our first sample here, given the following equations in x and y, determine if the equation is a function or a relation, show your work, and explain your findings. So what we're going to do, we're going to start by solving this for y equals. So these a and b are both currently in implicit forms, and we're going to get them into explicit form. So for a, I'm going to factor out the y. So I have y times x plus 3 equals 6. I'm going to divide both sides by x plus 3. And we get y equals 6 over the quantity of x plus 3. Now we might recognize this from our previous studies. This is actually a rational function, and where x can't equal 3, or we have a vertical asymptote at 3, and we have a y-intercept at 2. So a quick graph of that function. Again, we have a vertical asymptote at x equals negative 3. I think I said positive 3 earlier. We have a y-intercept at 2, so here's the graph of our rational function. And you can see that for every x, there's only one y, and so this is a function. For b, if we divided both sides by 9 here, you might recognize this. This is going to be a hyperbola, and it is going to open up, if you will, on the x-axis, and it's going to look something like that. Now we can see here that this is going to fail the vertical line test. For a given x, we will have two different y's, so this one is going to be a relation. But let's go ahead and put this in the form that we're looking for, in explicit form, and see what that one looks like. So we'll subtract y squared from both sides and then divide by the negative 1. So we get y squared equals positive x squared minus 9. And then we take the square root of both sides, and we get y equals plus or minus the square root of x squared minus 9. So this is a relation. We could see it from what we knew about the graph. For example, if we put in an x value of 5, if we put 5 in, we would get positive 4, but we could also get negative 4, plus or minus 4. So this is not a function. Example 2 asks us to construct a graph from the solutions. We kind of did that in the previous one, but let's go ahead and follow the directions here. It says solve the equation for y in terms of x. So I've got a GCF here of y, so I can factor that out, and I get y times x minus 2 equals 4. Divide both sides by x minus 2, we get y equals 4 over x minus 2. Again, we have another rational function that we know how to graph because we did that in previous studies. So we know that x can't be 2, so we have a vertical asymptote at 2, and we put 0 in for x. We get a y-intercept of negative 2. If we test for our limit as x approaches plus or minus infinity, we know the limit of this function is equal to 0. This is going to get closer and closer to 0. So we have a horizontal asymptote at the x-axis, and our graph is going to look something like that, and we've got a good enough picture here, and so we don't even need to find those solutions. We've got some key ones here. 0, negative 2 is probably the best one that we need, and all the other ones we can just sketch. In example 3, can the equation x squared plus y squared equals 16 represent a function with an input value of x and an output value of y, where y equals f of x? It says to support our answer with algebra. Well, we can do this, but we know already this is a circle. Okay, so this guy is going to be a circle. It's centered at the origin, and the radius is 4. So I've plotted points for my circle. I've taken my equation. We want to solve it for y equals f of x. So we have x squared plus y squared equals 16. Subtract x squared from both sides. Take the square root of both sides, and we get y equals plus or minus the square root of 16 minus x squared, which is a circle with a radius of 4. It's a really bad circle, but it'll look something like that. In example 4, we want to solve the equation for y in terms of x. So I'm going to subtract x cubed from both sides. I get negative y squared equals 8 minus x cubed. Divide it all by negative 1, and we get y squared equals x cubed minus 8. And then we take the square root of both sides, and we get y equals plus or minus the square root of x cubed minus 8. Use a calculator to sketch the graph at the right. So let's take a look at what this would look like on our graphing calculator, and we'll go ahead and sketch some points. So after I put that into Desmos or my graphing calculator, you can see that the positive square root of x cubed minus 8 will give me all the ones above the x-axis, and the negative one will give me the green line, will give me the values below the x-axis, and then we can transfer that over to our video notes. Keeping in mind our restrictions, we have the square root of x cubed minus 8, so we can't have a real result if this is a negative value. So x cubed minus 8 has got to be greater than or equal to 0. So x has got to be greater than or equal to 2. So doing a table of values, if I put in 2, I'll get 0. And if I put in 3, I'll get plus or minus the square root of 19, which is about 4.5. And if I put in 4, I'll get plus or minus the square root of 28, which is just a little bit more than 5. So we do get 4.5. I misplaced that. And then put in 4, we get a little bit more than 5. And so we get our graph that looks something like that. In example 5, we're asked to describe the graph of this particular relation, x squared minus 2xy plus y squared equals 25. Can you factor and find the solutions? Sketch the graph of the relation at right. Well, we should be able to factor that. That actually is a perfect square trinomial. It follows our pattern a squared minus 2ab plus b squared. So that is a perfect square trinomial. This factors to x minus y quantity squared equals 25. If we take the square root of both sides, we get x minus y equals plus or minus 5. So we get two equations, x minus y equals 5 and x minus y equals negative 5. These are lines. Some of you guys might want to write it into y equals mx plus b. I'm just going to find my x and y intercepts. If I put 0 in for x, y is negative 5. And if I put 0 in for y, x is 5. So I can plot those points. And for x minus y equals negative 5, if I put 0 in for x and solve for y, I get 0, 5. And I put 0 in for y and solve for x, I get negative 5. And we have two lines that are parallel. They have the same slope, but different y-intercepts. And it does fail the vertical line test, right? If we put 0 in, we get either 5 or negative 5. So that is definitely a relation. It's a set of parallel lines with a slope of 1. And that wraps up our introduction to implicitly defined functions. And you'll get some more practice with this when I see you in class.